going to stop asking you questions. 13A is EM induction. 13B is national grid. And 13C is energy and transformer. Okay. 13A. EM induction is literally how can I induce a potential difference. Instead of in chapter 12, I'm the one providing electricity to create magnets. How can I create electricity myself? Okay? I either have to have a conductor close to a moving magnet or a magnet next to a moving conductor. As long as there is motion between a conducting wire and a magnet, I can induce potential difference and therefore current if I close the circuit. Okay? So EM induction is simply changing or moving magnetic field cutting through a conductor induces a potential difference. Okay? So you either have a fixed magnet and move the wire, so it cuts through, induces PD, or you keep the wire still and you move the magnet in and out or close to the conductor, induces PD, or the magnetic field on this magnet, if I just fix it to my coil, the magnetic field changes. Either gets turned on and off, or it changes its direction constantly, will also induce PD and current into my coil. Yeah? Okay, so moving or changing. What do we know about the direction of the induced potential difference?
Said you're not going to ask this question.
What do I know from Lenz's law about the induced potential difference in a conductor? It will always be created in a direction to oppose whatever created it. Okay? Because remember, if I put a magnet into a coil, okay, north, south, north moving in, this magnetic field from the permanent magnet is going to make the electrons in the coil move in a certain direction. It's going to induce potential difference, induce current, okay? Because the field's coming in, it's cutting through the conductor. The direction those electrons move will create their own magnetic field in the solenoid, such that that magnetic field opposes the magnet creating it. If the magnet is coming in and north is coming in, how does the solenoid oppose that? It sets up a north on the same side, so it tries to push it out. If north was going out, what would be on that side?
South.
Put a south there to pull it back. Okay? If south was coming in, what would happen? It would put a south there to try and push it out. So it would always create a current so that the direction of the current makes this field, induces a magnetic field, so that it opposes the change. It always opposes the change. Okay? And the reason that there is a magnetic field here is because a magnetic field, a permanent magnet, is coming in and it is inducing a current in the wire, and if there is a current in a wire, then there's a magnetic field. Okay? How do I increase the amount of potential difference that I can induce? Move magnet faster, increase the number of coils, or use a stronger magnet. Yeah? 3 ways to increase the amount of potential difference. EM induction is about inducing potential difference, which leads to induced current. If I want to increase this, move magnet faster, stronger magnet, or more coils. Okay? 13B is the national grid. The first part of 13B is the transformer. Oh, I missed a bit. I missed a lot. Generators, 2 types.
We didn't take note.
AC alternator, DC generator, dynamo. Remember, these generate potential difference and electricity. If I want to create AC current, I use an alternator. If I want to create DC, I use a dynamo. What does the alternator use in order to make sure it's AC that's produced? Slip rings. What does the dynamo use?
Commutator.
The commutator. Don't get yourselves commutator. Don't get confused, just use slip rings and commutator. Do not worry about the split ring. Okay? They both use coils. Both energy transfers are kinetic in, so obviously we have to find ways to make the coil turn, make the generator turn in order to produce the electricity. Slip rings for AC, commutator for dynamo. Microphone and loudspeakers. Okay? Microphone creates sound. The pressure in the air gets transferred by vibrations to the diaphragm of the microphone. When it hits the diaphragm is going to vibrate in the same way as the sound of the air outside is vibrating. If the diaphragm is connected to a coil, the coil moves, or pulsates if you want, forwards and backwards around a permanent magnet. In that coil, a potential difference in current is induced. So that is electromagnetic induction. If there's a coil moving around a magnet because the diaphragm is vibrating due to the sound, then it is inducing current in the coil. Okay? And that current is AC because the coil is moving backwards and forwards because the sound wave vibrates like that. That current is transferred to a loudspeaker. So the loudspeaker also has a coil with a magnet and a diaphragm. It's designed slightly differently and bigger so that the sound is louder. When the AC goes to the coil, okay, AC comes in, you have current changing directions in a coil, which means there is a magnetic field induced in the coil, like a solenoid, in a changing direction. What happens is the magnet inside the coil, the motor effect occurs, and the coil moves again because the coil's magnetic field interacts with the permanent magnet inside the coil. Okay? Because the current is AC, the magnetic field produced is AC, and therefore the motion is forwards and backwards, moving the diaphragm of the loudspeaker forwards and backwards and amplifying the sound. So in a microphone, electromagnetic induction occurs. You produce the sound, the forces, and they induce potential difference in AC current. In a loudspeaker, the input energy is electricity transferred by forces to sound. Yeah? So it's the opposite direction. The one that is most like a generator is which one? Microphone or loudspeaker?
DC.
Generator uses EM induction where current is produced. That's the microphone. Which type of generator is most like a microphone? AC. Okay? Because it produces AC current in a microphone. Doesn't use slip rings and a rotating coil. Just moves a coil moving forwards and backwards around a fixed magnet. Okay? 13B is the national grid. The transformer is basically the main component of the national grid in terms of how it works. Okay? So the national grid is used to create electricity at a power station, transfer it all the way across the country, and distribute it into different places by wasting as little energy as you can from power station to homes. Okay? The best way to do that is using this thing called a transformer. Now, into the transformer goes AC current from your power station, for example. If AC current passes through a coil, what do we know is created around the coil?
Magnetic field.
Magnetic field. If I connect this to a rectangular iron core, that magnetic field is induced. So you induce magnetic field at the primary coil because you have a change in current, so it induces a magnetic field like a solenoid. But the rectangular core focuses that field. Is the magnetic field produced changing or staying the same?
Changing.
Changing because it's AC. So the direction of the magnetic field changes. What does that cause in the secondary coil?
It moves the magnetic field to the secondary one. It induces electricity.
Exactly. Because you have a changing magnetic field passing through this coil, you are inducing a potential difference and current in the secondary coil. So I put the AC into the primary coil from my power station. The changing current in here produces a changing field in the core. The changing field in the core induces a changing potential difference in the secondary coil. Okay? And therefore we get AC out. Now what's the point? You can either step up voltage or step down voltage.
If you step up, you have more coils on the secondary.
Yeah.
And the other way around.
If you step up voltage, you have number on the secondary is greater than number of turns. All you need to do to increase voltage across a transformer is wrap more turns of wire around the secondary coil. If you want to reduce the voltage across a transformer, you just wrap less on the secondary. It's that simple. So secondary is greater than primary for step up, secondary is less than primary for step down. The transformer equation is voltage in the primary over voltage in the secondary is equal to number in primary over number in secondary. Okay? It's given to you at the back of the exam, you just have to use it. Whichever one you want, if it's VP or NP, all you have to do is multiply once to find it. So for example, if I'm looking for NP, I'll be given this, this and this, I multiply NS to the top, and I found that. If I want one of the bottom ones, I flip both fractions. So for example, if they ask me for VS, I'll turn them both upside down, and I'll just have to multiply the VP from the bottom to the other side. So it's either multiply once, or flip and multiply once. It's that simple. Okay? So that's the transformer. Step up, step down, number of turns, secondary is more, secondary is less. The national grid itself, we come from the power station at 25 kilovolts. We step up immediately to 400 kilovolts for the transmission lines, which are the cables that transport the electricity across the country. Okay? Why do we step up to such high voltages? So to reduce the amount of energy wasted by heating in the cable. Okay? We get to the end of the transmission lines, we step down, 33 kilovolts for factories that are big, 11 kilovolts for factories that are small. We carry on from the first step down, we step down again to 230 volts for mains voltage in homes, schools, offices, etc. Okay? The main reason we step down to such low voltages is for safety and for increased current. Okay? That's 13B, the national grid. This transformer is obviously the device that kind of holds the national grid together. Okay? That's the equation. Last one, we have three equations. Power equals energy over time. Electrical power in a circuit equals IV. And power loss in a cable or circuit equals I squared R. The power in a transformer, I times V, you'd have I primary, V primary, okay, and I secondary, V secondary. Because this device, in the secondary coil, whatever power you have here was created by the primary coil, power in a transformer is conserved, okay? So the power in the primary must be the same as the power in the secondary. It cannot be created or destroyed. So IPVP equals ISVS. That's another equation. Again, it's in the back of the exam. Okay? This one's even easier. If I want VS, I have all three of those. All I do is divide once. No matter which one of these in the equation I want, I only have to divide once, whichever one I don't want. Yeah? Okay? Because of this, I know in a step-up transformer, the voltage will go up. So voltage on primary will go up to voltage on the secondary. But if this is to remain the same, what happens to current across the transformer? It goes down. So if voltage goes up in a transformer, current goes down in order to maintain this equation or to conserve power. Okay? Why is that useful? Because in the national grid, straight after the power station, I had 25 kilovolts. Okay? I stepped up to 400 kilovolts, so that means that the current was taken right down. The reason being, the transmission lines take the electricity the farthest distances that the electricity will travel. You're going to lose a lot of energy due to heating. The reason you lose energy due to heating in a cable is because of the resistance of the cable. Electrons are colliding with the protons or the positive ions. Okay? In order to reduce the amount of collisions between electrons and ions, positive ions, is to reduce the current. Okay? I could have cooled it down, but it's not practical. I could have used a better conductor, but I'm sure we're using the best conductors we have. And I could have made them thicker, but that only goes so far before it becomes impractical. A very easy way to reduce the collisions in the cable to reduce heat loss is to reduce the current. And I can do that with the transformer. If the voltage goes right up, the current will go down, less collisions, less energy wasted due to heating. The equations that I'll need to do a calculation for in the exam question could be power is energy over time, power is IV, or power loss. So P equals IV tells you what is the total power in the cable or in the national grid. P equals I squared R tells you how much power is lost due to heating or how much energy is lost per second due to heating because of the current in the cable and the resistance of the cable. Okay? And that's it. Are there any questions? You have -3 minutes. If you have a question, just ask now. I can stay for 5, that's fine.
What's a carbon?
What's a? It's just a conducting material that connects to the coil on a motor or a generator. Alright, we don't use metal because they grind. So we use a conducting material, but it can touch the coil, the slip rings or the commutator, can allow it to turn and touch without grinding away. Okay? Any other questions?
What's the purpose of a commutator?
Commutator is simply there in order to allow DC current through the coil, okay, the motor, so that the positive and negative terminals stay in position, but the coil can rotate inside. So you always have current going down this way and this way. It turns over and it goes down that way and that way.